Well, hello everybody. Nice to be with you again. We're going to have a look at some applications of derivatives of circular functions. Wow, that sounds pretty exciting. And it is. But what functions, you may well ask? Well, we're going to do some sines and some coses. Happy little sines and coses they are. And when you finish looking at this stuff with me today, you're going to feel like that. Or maybe like that. But it's loads of fun. So let's get into it and see what we can discover. Now these get from sort of routine to a bit industrial strength. But fear not, armed with our trigonometric toolkit of little spanners and wrenches and things, we'll just take care of it, don't you worry. Now this one here, it says find the equation of the tangent of the curve with equation y equals sine x at the point where x is pi on 3. No problem. Now as you know, a tangent line has the form y equals mx plus c, as any straight line has that form, where m is the gradient and c is the y-intercept. Okay, now, so we need m, we certainly do, and we need c, we certainly do need that too. But it's no problem for you and me because we're going to just do some differentiation throughout the nation. To find m, what we're going to do is we're going to take the function itself and we're going to differentiate it, and that will give us the gradient function. And then we plug in x is pi on 3, we're going to get the actual specific value of the gradient at the point when x is pi on 3, which, wouldn't you know, comes out to be a half. Okay, so now we've solved the puzzle of m. So we know that the tangent line is now y equals a half x plus c, but we still have to find what c is. So, no problem. What we're going to do, as you know, to solve that little equation above for c, we need a value of x and a value of y. Well, no problem. We know that x is pi on 3, we've just got to find y by plugging it into the equation y equals sine x. And that comes to root 3 on 2. Now you knew that, didn't you? Yes. Own up if you didn't, because it's time to go and learn it if you didn't. So, alright, let's keep going. So therefore, what we're going to do now is we're going to sub that point. That's when x is pi on 3 and y is root 3 on 2 into that equation for the tangent to find c. And there we go, and c will come out very easily, and there it is. So there is our equation coming up. The tangent line is this little beastie, and it looks very, very nice. Mr. Box, thank you, Mr. Box. Ah, how sweet it is. Now, is that all we have to do? I think it is. Excellent. Right, let's move on. Oh, of course. Yes, and it's thumbs up. Did you know that came from the Romans, that thumbs up business? That's when they were feeding people to the lions. Rather nasty. So, but thumbs up for us. We did a good job. Find the equation of the tangent and the normal this time of the graph y equals minus cos x. That's a pretty similar sort of question, except we've got to find the normal as well. Okay, let's do the tangent first. Same procedure as before, actually. I'm calling it y subscript t because I don't want to confuse it with y, the function y, which is minus cos x, if you know what I mean. So let's go for the m, which we need, and the c, which we need. I think we'll go for m first, shall we? Yeah, good. So same procedure as before. We know that y is minus cos x, so we differentiate that. dy dx is minus sine x, which comes out to plus sine x. Now, what we've got to do now is find the actual value of that gradient function when x is, what is it? Pi on 2. Yeah, okay, so we go for that. And we get, of course, you know that sine of pi on 2 is 1. Yes, and therefore that gives us our gradient, our specific value of the gradient of that function when x is pi on 2. So we've got our tangent line now is y tangent equals 1 times x plus c, and we still have to find c. So now we're going to do through the same procedure as we did before. We're going to sub x is pi on 2 into the actual original function y is minus cos x to get the y value. And that, oh, it's naught. y is minus cos pi on 2 is naught. Well, that's very interesting. So that means we've got our point. We've got pi on 2 and naught. Okay? So we sub that in to our equation for is a tangent, and we'll find c as a result of that. Okay, there it goes, and therefore it looks like c is minus pi on 2, guys. So we've got it all. We've got m and c for you and me, and there's the equation of our tangent. Mr. Box, thank you, Mr. Box. Now that's it. That's it. Oh, hang on, we still need the normal, don't we? Okay, Mr. Normal, let's do you now. Now, I hope you remember our little very important rule for perpendicular lines, gradients of perpendicular lines, because we know the gradient of the tangent is 1. And we know that for perpendicular lines, we know that m1 times m2 is minus 1. And we know if we choose line 1 as the tangent line to the curve, then in order for that equation to come out to be true, m2 would need to be minus 1. Wouldn't it? That's right. Of course it would. Just had a momentary lapse of concentration there, guys. Yeah, there it is. So now there we've got the gradient of our normal line now, and all we've got to do is find c. Yeah, there it is. Y of the normal line is minus 1 times x plus c. We've got to find c by subbing in that same point, guys. Yeah, that point there, and what do we get? Sub it in. Oh, look, that's interesting. C is plus pi on 2. Very interesting. Now, I think I've run out of room, so I probably have to go over the page. Yes, I did. And now, that's where we got to. Oh, that's where we got to. There it is. There it is. Now, I think Mr. Box is coming. Hello, Mr. Box. Thanks again. Mr. Box is so reliable. Thank you, Mr. Box. Now, what I've done for you, I decided to give you a special treat. And that special treat is I actually went and did them on the graphical CAS calculator to show you how incredible it is. Okay? Now, watch this. Ooh! Look at that. Work of art. Now, the blue line is the original function. That's minus cos x. Satisfy yourself that that is minus cos x. Go from the y-axis. You can see it's an upside down cos function, isn't it? Now, this one here, the red line, is the tangent function. Look at it. It's definitely a tangent. Definitely a tangent when x is pi on 2. Yeah? So that's very exciting. And the other one, the black line, is the normal. That's minus x plus pi on 2. Pretty exciting, eh? How do you like it? So it all works, you know. Maths is incredible. Maths is just a great, big, exciting game, which just excites us, no end, at every turn. So here we go. Oh, there's Mr. Thumbs Up. Hello, Mr. Thumbs Up. Now, as long as we don't get the thumbs down, we'll keep going. What do we got here? F of theta is sine 2 theta. If theta is increased by a small amount h, here we go. So you see that word approximation? What does that tell you, guys? Linear approximation. That's what it is. Okay. Now look, I think in order to help you understand this, I think I'm going to draw a little graph to help you. Now, here we go. See, that looks like a little bit of a sine 2 theta kind of graph, doesn't it? It looks like sine anyway. There's y, there's theta. There's my pi on 6 point, and there's my pi on 6 plus h. H being a little bit, okay? So there's the tangent of the graph, that is y is sine 2 theta at theta is pi on 6, right? And there is h. There is h, okay? Now, this bit here that is the delta f. That's the change in f of theta, the approximate change in f of theta, not the actual change in f of theta, but the approximate change in f of theta over that distance h from x is pi on 6 to, or theta is pi on 6 to theta is pi on 6 plus h. So that's the thing, and you can see it's just the gradient times the run gets the rise. Remember, rise over run gets gradient, therefore gradient times run gets rise. Now, there is the difference. That's the error we're making by using this approximation technique. And you can see that we have done an overestimate. So please know how to do that, because you're likely to get asked in an exam how to do that. That little diagram's worth its weight in gold, plus a few little explanatory words, and you'll get full marks for something like that, where they ask you overestimate, underestimate kind of questions. All right, let's get into it. Here we go. A, approximation for f of theta plus h. All right, no problem. We know that f of theta plus h is approximately equal to the original value of f of theta, that is, in this case, where theta is pi on 6, plus the run times the original gradient. That's the rise, okay? That's the rise. Now, we've just got to use that formula, and we're on clover. Everything will come up roses. So now, f of theta is sine 2 theta. So we want the gradient function, that's 2 times cos 2 theta, isn't it? Yeah, you satisfied with that? Now we're going to sub some values in. So when theta is pi on 6, we need to know what the gradient will be. And it's going to be 2 times cos of twice pi on 6, or pi on 3. Now, cos of pi on 3 is a half. So it's 2 times a half, which gets you 1. So that is the actual gradient of the function sine 2 theta when theta is pi on 6. You get it? Right, it's got a gradient of 1. Now, we also need to know what the actual value of the function is. Not the gradient, but the actual value when theta is pi on 6, and that will get us sine of 2 times pi on 6, which is sine of pi on 3, which happens to be root 3 on 2. Now I think we've got all our ducks in a row, guys, and I think we can probably plug and play and save the day. Hooray! Hence, substituting into that thing that looks so nasty but is actually an easy little friendly little beastie, we're going to get the answer. So there's f of theta plus h is that which comes from there. See where I just did the little blue circle above? And that which comes from down there. See the purple circle down the left-hand bottom? Hey, now come on, don't tell me that's hard. It isn't hard. So there's what you get. Now, of course, that's approximate. It's not actual. It's the approximate, because we're using linear approximation. Mr. Box, thank you again, Mr. Box. You're a marvel. Now, that's part A. We've saved the day with part A. Hip hip hooray. Now, let's do part B for you and me. Oh, I'll stop, sorry. All right, so there it goes. Expression for the percentage change. Well, look, the percentage change is just the fractional change multiplied by 100. The fractional change is delta f over original f. Did you get that? I'll just write it out for you. Now, delta f is just the second part of that expression that's now got a red circle around it over there. It's just the increase in f, the approximate increase in f, which we know, as we know, was h times 1. Now, the original value of f was, it was root 3 on 2, wasn't it? So we're just doing delta f, which is h, over root 3 on 2, which is f, and that's the fractional change. So now we have to multiply that by 100 to get the percentage thingy, and what does it come to? There it is, guys. Now that's not hard. 200h over root 3. Don't have to rationalise that, by the way, just leave it alone. And Mr. Box, thank you, Mr. Box. Now there you go, we've done it. Linear approximation throughout the nation, and it was great. Alright, okay, onward ever onward. Oh, Mr. Thumbs Up, thank you. Now, what's this thing? Find the local maximum and minimum values of f of x equals that funny looking thing. Well, this is a max-min one now. Look, we're throwing a bit of everything at you today, aren't we? We've done gradients and normals, we've done linear approximation, all with trig functions. Now we're going to do this funny thing. This is max and mins now, and I can tell you, I'll give you a hot preview. What's coming after this is going to be some chain rule and related rates My goodness, how exciting. But let's do this one first. Max and min. Well, that means we've got to take the gradient, don't we? And then set it equal to 0. Yes, I hear you say. So let's do that. Yeah, we know we've got to do that. Let's do it. So f dash x now is that thing. Oh, now, did you see that second term on the right-hand side of that equation? How did I get that? Chain rule. Chain rule. Okay, if you're not sure, you better go back and learn your chain rule, okay? It's like saying something is 2 times blob squared. Then the derivative of it is 4 times blob times d blob dx, where blob in this case is sine x. Now, if you didn't get that, you better do a replay and replay me, because that's what it is, guys. It's that simple. Okay, now we're going to set that thing equal to 0, and what are we going to do with that? No problem. I'm going to factorise, so I'm going to take 2 cos x out of those both terms, and what am I going to get left with? That thing. Now, the good old null factor law is going to take over now, and we're going to say that therefore cos of x is 0, or 1 minus 2 sine x equals 0, and we have to solve for those situations, because that's going to be our answer. It won't tell us whether they're maxes or mins, but it'll tell them whether they, it won't discriminate between which ones are maxes and which ones are mins, but it will certainly capture all of them. Yeah, the second one comes to sine x equals a half. Okay, off we go. That's number A, and that's number B. Now we'll do A first of all. Here we go. So cos x equals 0, and we've got x goes from 0 to 2 pi. 1 revolution, guys. Now, can you think about what that looks like? Think of your cos graph. Come on, you know what it looks like. Of course it looks like that. So you can see when it's equal to 0. There they are, you see? Of course they are. So x is pi on 2 or 3 pi on 2, which gets you a 0 value for cos. Alright, now here comes B. 1, 2, 3 for you and me. And sine x equals a half. Okay, well let's do a quadrant diagram for this one. The basic angle in quadrant 1 for sine being a half is pi on 6. Now, there's my fairly primitive quadrant diagram. And okay, for sine being positive, we want quadrant 1, quadrant 2. So there they are. There they are. Those angles are the ones I want. So there's a pi on 6 in quadrant 1, and of course that comes to 5 pi on 6 in quadrant 2, taken from the 0 position, if you get what I mean, yeah? Alright, so therefore, what am I saying? X therefore has to be pi on 6 or 5 pi on 6. Therefore, I've got my 4 angles, haven't I? Hence, for maxes and mins, we know that X has to be that pi on 6 or pi on 2, that one, or pi on, I'm just circling them. You can see I'm circling them from where they came from. 5 pi on 6, that's that one, and that's 3 pi on 2 from the lower left hand corner, and we've got them. But of course, guys, don't go rushing off and thinking you've answered the question. Please reread the question. You've solved for x, you think you're finished, but you're not. Look, what do we got to do? We've got to find the local maximum and minimum values of f of x, not the x values at which they occur, the actual values. So we've got to go plugging in the values of x we've found into the values for that function, and we get all the successive answers, okay? That's pi on 6 I've just done for you. Pi on 2, plug and play, that comes to 1. 5 pi on 6 comes to the same thing as pi on 6 did, but the last one doesn't. 3 pi on 2 is not the same as 4 pi on 2 actually. It comes to something quite different. So there's your 4 values for f of x. So there we go. Local maxes and mins are, they're the values. 3 on 2, 1, 3 on 2 and minus 3. And we can't say whether they're maxes or mins, but we know that they're either of the two, maxes or mins, yeah? Mr. Box. Thank you, Mr. Box. Good heavens above. How are we going? It's very exciting, isn't it? Oh, Mr. Thumbs Up, thank you. Now this one here is a very, very nice question. This is a ladder. It's a it's a pole. Oh, okay. It's a 5 metre pole leaning against a vertical wall. And the lower end of the pole moves away from the wall at a constant speed of a metres per second. Find for the instant that the foot of the pole is 3 metres from the wall, and I presume moving to the right in that diagram, because it's slipping away. Certainly wouldn't move the other way unless we're on a different planet, and because gravity is working on it, okay, if you know what I mean. Alright, so what are we going to find? A, the speed at which the top of the pole is descending, and B, the rate at which the radian measure of the angle defined by, that's theta in that diagram, by the pole and the horizontal, between the bottom of the pole and the wall, what? The rate at which the radian measure of the angle defined by the pole and the horizontal, between the bottom of the pole and the wall, yeah, that's the, yeah, I get that. It's just theta, guys, is changing, alright? Let's do A. Now, what have we got to do? The speed at which the top of the pole is descending. Now, look, I think I need to label this diagram, so that I know what I'm doing. So look up to the top right. There's x and there's y, okay? Now, they're telling us that dx dt is a metres per second, okay? So that's going to be plus a, because it's moving to the right in the positive x direction, isn't it? We need to get all that sorted out in our head before we start making mistakes. What they're asking us for, guys, is dy dt, okay? That's what they want, and we're going to give it to them. Now, okay, first, this is my standard technique of related rates questions, guys. Question 1. What do we know? Answer to question 1. We know dx dt is a metres per second, right? That is what's going to go on the left-hand side of our related rates chain rule expression. Now, question 2. What are we asked for? Well, funny you should ask. They want dy dt, okay? Now, that is all we need to know. We're going to set up our equation. We say dx dt, which is the one we know, is dx d something times d something dt. And what goes on the something? You look above. It's what they want. It's the y. So therefore you put y as I've shown you there. And we're all set up now. Now let's analyse what we have to do. This one we know. That's a metres per second. This one we want, so we're not doing anything with that at the moment because that's the one we have to find out. This middle one we need. So the rest of the question is going to be concentrating on trying to work that thing out, all right? A relationship between x and y, a derivative kind of relationship. Well, come on, have a look. Have a look up at that diagram in the right-hand top corner. Okay, I've got it. Have you got it? Dear old Pythagoras is going to come to the rescue. So, we know that x squared plus y squared is 25 because it's a right angle triangle. X squared plus y squared equals the hypotenuse squared, and the hypotenuse is constant at 5. Okay, so that enables us to solve that for y, and then that enables us to do dy dx. It's as simple as that. It's as simple as that. We cancel out the 2's, and what do we get? Dy dx, da-da-da-da. But we don't want dy dx, do we, guys? What do we want? We want, look back at that chain rule expression, we want dx dy. Oh, why, oh, why? That's what we want. Now, I think we're all ready to plug and play now, because that is the relationship we were looking for, the one we needed. And it was so simple. I'll call that equation star, and we'll plug and play. Substitute into that expression, yes, we will do that. Therefore, a, which is dx dt, equals that thing with the square rooty thing in it, that is dx dy, and then times dy dt. And of course, we have to solve it for dy dt. Okay, let's do that for you and me. And, now the thing is, we should be able to put a value of x in there. A has to stay as a, because that's the way they defined the thing. But you know, x is supposed to be 3. So let's, come on, we'll plug that in. What do we get? That's pretty good. Now, look, the square root of 16 is 4, so let's simplify that. But now, herein lies the enormous booby trap of this question, guys. Don't just rush off and put that as your answer. Look at the question again. It says the speed at which the top of the pole is watting. Not changing, it says descending. Descending. So there's an implied minus in that word. You see? So you have to say, therefore, it is descending at 3a on 4 metres per second. Not minus, but it is going down at 3a on 4 metres per second. Mr. Box. Okay, now they're likely to hit you with that in an exam, so just be jolly careful, please. That's really important, those descending kind of things, you know. All right, we did it. It's pretty exciting, isn't it? Now, I think we'll go over to the next screen and do B now. Okay, what have we got? Oh, right, okay, B. Now we want to know the rate at which the radian measure of the angle, that theta, is changing, not decreasing, it's just changing this time, okay? So changing is all right. We just do d theta dt. Now, same old routine. Let's come on. Look, we're going to do it. You should be getting used to it now. Question 1. What do we know? What do we know? Okay, answer. We know dx dt, which is a metres per second. Question 2. What do we want? What are they asking us to find out? They're asking us to find out d theta dt, aren't they? Of course they are. Well, that tells us how to do our chain rule equation. We start off with what we know on the left-hand side. Dx dt is dx d something times d something dt. And what is the something? Look above. That is the something. There it is. Thank you, Mr. Theta. Now, let's analyse. Come on, what do we know? Yes, we know you're A. And what do we got to find out? Yes, that's what we've got to find out. So we're just leaving you alone because we're going to solve for you. But this one in the middle is what we need. So the rest of the question gets devoted to that. Now, how are we going to work that out, guys? We need a relationship between x and theta, or theta and x, which we can take the derivative of. I think I can see it. Look at the diagram. Come on, look at the diagram. Oh no, don't look at the diagram. Sorry, x is 5 cos theta, isn't it? Because cos theta is x over 5, isn't it? It's that easy. Come on, you can do dx d theta. Dx d theta is minus 5 sine theta. That's it. That's it. Okay? Now, we might need to work out what the specific value of sine theta is, but we're not going to worry about that now. We've just about got ourselves sorted out. So, therefore, we're going to substitute what we've got into that star equation. I just labelled it star, the one halfway down on the left-hand side. Now, here we go. Right. So, therefore, A, which is dx dt, is minus 5 sine theta, which is dx d theta, times d theta dt. Now, solving for d theta dt gets us that funny looking thing. Now it's time for us to get our theta sorted out, guys. Now, yes, we do need that. However, if you look at the diagram now, you'll see it'll all unfold in front of you. Look at the diagram. Look, that's 3. Now, come on. Can you do a Pythagoras for me and work out what y is when x is 3? What is it? Of course it is. It's 4. So now, come on, what's sine theta? Yes, it's 4 over 5. There you go. Isn't that nifty? It's marvellous, isn't it? So, therefore, we've got this thing scun, absolutely scun. So, therefore, d theta dt is, yes, it is, and some cancelorama happening. And what do we get? Minus a on 4 radians a second. Now, look at the question. Make sure you haven't messed anything up. No, it's the rate at which the radian thing is changing. The theta is changing, not decreasing or anything. So minus a on 4 is appropriate. I think Mr. Thumbs Up's coming to say a final salute to us. Yes, thank you, Mr. Thumbs Up. You're a gem too. All right, guys, we got that done in under half an hour, which I think is pretty jolly good. So, Thank you for listening to my little presentation, and we'll look forward to some more exciting stuff coming up in the near future. Okay, bye-bye.